All right, let's continue answering the questions. Next question is, explain why two parallel wires carrying current in opposite direction repel each other. So let's draw two parallel wires. One wire is this one. So let me draw this wire with blue. So wire 1. And second wire is red. Let me draw it by red color. So these two wires are carrying current in opposite directions. So this is the second wire. And let me give directions. So let's say this is direction of the electric current here is down to the plane of the page. Let me say I2. And for the first one, direction of the electric current is up to the plane of the page, I1. Let me say this. So why these two wires repel each other? We are going to try to get this. Okay, remember, each wire carries a current. So if a wire carries an electric current, it must form a magnetic field around. So both first and second wire produces a magnetic field around themselves. So let's start with the first one. This first wire produces a magnetic field. So according to right hand rule, I can find the direction of the magnetic field around the first wire. Thumb is pointing in the direction of the electric current, which is up to the plane of the page. So this forefinger must point magnetic field direction on the right side and magnetic field direction on the left side. So on the left side of the first wire, so it is out of the page, but on the right side, it is into the page. So I should check the right side because the second wire is on the right side of the first one, because these two wires affected by the magnetic field of one another. So magnetic field of the first one affects the second wire. Magnetic field of the second one affects the first wire. So that's why we should locate the forefinger just where this other wire is. So if I want to find the effect of the magnetic field of the first wire, I should find what is direction of the magnetic field on the location of the second wire. So it is into the page. This first wire produces a magnetic field here on the second wire, which is into the page. So this is B1. Why B1? Because it's made by the first wire. After that, we're going to apply the right hand rule for magnetic force acting on a wire. Remember, it was like this. Forefinger is the magnetic field direction, thumb is the electric current direction, palm is the force acting on the wire. So now let's apply it. Magnetic field is into the page. So this is the into the page. Thumb is direction of the electric current. Electric current on the second wire is down to the plane of the page. So magnetic field is into the page. Thumb is pointing the down to the plane of the page. Palm is pointing to the right. So that's why this second wire, wire 2, experience a force to the right because of the magnetic field of the first wire, B1. So this magnetic field, the second wire's electric current is I2, length of the second wire is L2. So then this wire will be repelled. Second wire will be repelled by the first one to the right. So the same thing happens for the first wire. So because second wire makes a magnetic field on the location is a chapter question, question number 18. It's asking that a stream of electrons is projected horizontally to the right. So we are going to first we say stream of electrons means billions of electrons. They are projected to the right. So they are going to the right like this. So let's look at these are electrons. These electrons are moving to the right. So projected means thrown to the right. They are traveling to the right. A straight conductor carrying a current is supported parallel to an above electron stream. So we are going to locate a straight conductor parallel to this electron stream. So this is the stream of electrons. This is the straight wire. And what is the effect on electron stream if the current in the conductor is from left to right? So electric current will be from left to right. So like this. Electric current on the conductor will be from left to right. So then what happens to the electron stream? Question is asking this in part A. So then because electrons are moving from left to right, electric current of this electron must be from right to left, because we know that electron motion, electric currents are in opposite directions. So if the electrons are moving to the right, electric current of this electron must be from right to left. Look at the direction of these two electric currents. One of them is to the right, the other one is to the left. Two currents are in opposite directions. What happens if they are in opposite directions? They will attract one another. Because the conductor is fixed, it does not move, but electrons are free. So these electrons will be attracted. So they are opposite in directions. So these two currents will repel each other. Because electrons are free, these electrons will be repelled by the conductor. So that's why electrons will start moving away from the conductor. So what is the effect if the current is reversed? It says that change the direction of the electric current on the conductor. So in this case, these two currents will be in the same direction. So both currents will be to the left. If two wires or two currents are in the same direction, they will attract each other. So this conductor will attract the electrons. That's why these electrons will, in this case, approach to the conductor. So this question is asked in a test bank. A little change I made in this question. A stream of electrons is projected horizontally to the right. So this time, electrons are also to the right. So these are electrons. They are traveling to the right. A straight conductor carrying a current is supported parallel. So a conductor is supported parallel and above the electron stream, as you see. What is the effect on the electron stream if the current in the conductor is from right to left? This time I changed the direction of the electric current in the question from right to left. Electric current direction on the conductor. Stream, electrons are moving from left to right, but electric current of this electron is from right to left because electron motion and electric current are in opposite direction. This is the electric current of the stream. So look at directions. Both currents are in the same direction. If two currents are in the same direction, they will attract each other. That's why this conductor will attract electrons. Now electrons will start approaching to the conductor. So the electron stream moves away from the conductor, not correct. The electron stream approaches to the conductor. This is the correct answer for this question. Next question is question number 24, which is a chapter question again. A proton moves at 2.5 times 10 to the power 6 meters per second horizontally at right angle to a magnetic field. So what is the strength of the magnetic field required to exactly balance the weight of the proton and keep it moving horizontally? The question which is asked in the whiteboard is not this part, second part. Should the direction of the magnetic field be in horizontal or vertical? This is the question which I should explain. But the answer is here, exactly balance. What does exactly balance mean? How can you balance this pen? If you release this pen, it falls down. Electron or proton, whatever. So when it's released in the atmosphere, it falls down because of the gravitational force. It's downwards. How can you balance this gravitational force by applying a force up to the sky? So magnetic force acting on electron must be up to the sky, upward to the sky. So if the force acting on the proton is upward, which is in vertical, because upward is vertical, of course, up to the sky means vertical. And we know that force and magnetic field always perpendicular to each other. If force is in vertical, magnetic field must be in horizontal, of course. So this is the answer of this question. So if you are balancing a charged particle which is more inside the Earth's magnetic field, which means you should apply a force up to the sky. If the force is vertical, which is up to the sky, So we know always force and magnetic field always perpendicular to each other. That's why magnetic field must be in horizontal. This is the answer of this question. Next one is question number 25. It's asking two currents run in opposite directions in two parallel wires A and B at a distance of 1 meter apart. So two conductors A and B carries opposite currents. If the current I is 1/3 of current B, determine the position of the point along the line normal to the wires where the total magnetic field is 0. So I'm going to draw wire A with blue and wire B with red. So they are parallel wires. Let me draw, this is wire A, which is blue, and wire B, which is red. Two parallel wires. They carry opposite currents, opposite directions. So we can give directions. One of them is up to the plane of the page, the other one is down to the plane of the page. It's up to you. I'm going to do like this. Down to the plane of the page is B. Let me say this is B. Up to the plane of the page is A. This is A. And question saying that A is AB over 3. Yani if I say that this is IB, so current of A must be, according to question, IB over 3. So determine the position of the point. Yeah, we are looking the point, location of a point, along the line, a line normal to the wires. So draw a line normal to the wires, which is, normal means perpendicular, where the total magnetic field is 0. So on this line, somewhere, total magnetic field must be 0. We are going to look here, here, or here, where the total magnetic field or net magnetic field is 0. And one more thing, we know that these wires are separated by a distance of 1 meter. It's given in the question. Okay, two conditions must be provided for total magnetic field to be 0. One of them, fields must be opposite in direction. Fields must be opposite in direction. One condition is that. This is all condition for all resultant to be 0, because if the directions are not in opposite direction, they cannot cancel each other. Second one is magnitudes must be equal. Magnitudes must be equal. Okay, so I'm going to look first at what location these two wires produces oppositely directed magnetic fields. So let's find it. So for wire A, thumb is pointing in the magnetic field direction. Curled forefinger is pointing on the right side into the page, on the left side out of the page. Right here, which is that wire A, makes a out of the page magnetic field on the left side of the wire, but into the page on the right side of the wire. This is only for magnetic field of wire A. But wire B, it has a current which is down to the plane of the page. On the right side, on the left side, it is into the page. So on the right side, it is out of the page. Directions are opposite. Here, on the right side, magnetic field is out of the page, but on the left side, it is into the page. So here, if you look at them, between these two wires, magnetic field of the A and B are in the same direction. They can never be 0 between the wires. Beyond wire B or beyond wire A, somewhere here or here, the net magnetic field must be 0. Where? Beyond B or beyond A. So always we should choose a point which is closer to smaller current. Which one is smaller current, B or A? A is smaller because A is AB over 3. AB, say 3, IA is 1. So you are going to choose a point which is closer to the smaller current. So I will say the distance from this smaller current carrying wire to this point, say P, X. Here, magnetic field will be 0. And distance from point to the wire is X. So I will now apply the second condition. Field must be opposite, first condition. Field must be equal in magnitudes. Let's calculate the magnitude of magnetic field because of each wire here. For wire A. So BA, magnetic field, mu IA divided by 2 pi distance dA. So magnetic field of the A, mu IA is IB over 3. IB over 3, it's given in the question, divided by 2 pi distance of A to the point. From A to the point, P, it's X. I said X because I want to find this. This is for wire A. For wire B. So magnetic field of wire B at this point P is equal to mu IB over 2 pi distance of wire B to the point. So let's write the given. Magnetic field of B. So mu IB 2 pi distance from wire to the point. 1 plus X. 1 plus X. So then magnitudes must be equal. These two must be equal to each other. Yani mu IB over 3 2 pi X, mu IB over 2 pi 1 plus X must be equal to each other. Let's make them equal. So mu IB over, let's get this 3 down, 2 pi 3x to the denominator is equal to mu IB divided by 2 pi 1 plus X. So simplify mu over 2 pi, and IB. So what's going to happen? 1 over 3x is equal to 1 over 1 plus x. Cross product, 1 plus x is equal to 3x. So 1 is equal to 2x, x is equal to 1 over 2, which is equal to 0.5 meters. So then, this distance must be 0.5 meter from wire A. Yani the point where the net magnetic field is 0 must be equal to 0.5 meter from the smaller current. So at this point, net magnetic field could be 0. Other question is, two concentric circular coils lie in the same plane. The inner coil has 120 turns of the radius 0.0012 meter and carries a current of 6 meter. The other coil has 150 turns and radius of 0.0017 meter. What is the magnitude of the direction of the current in the outer coil such that the resulting magnetic field at the center must be equal to 0? We have two coils, concentric coils, which means they have the same center. One coil is this, second coil is that. This is the center, they have common center. Concentric means common center. Inner coil has 120 turns. This red one, let me draw it a little thicker so that it's a coil, not a wire. There are so many loops. So inner coil is 120 turns. 120 turns. Radius is 0.0012 meter. Carries a current of 6 ampere. But outer coil is this one. Outer coil has 150 turns. Its radius is 0.0017 meter. So what is the magnetic direction of the current in the outer coil? We will find how much is the current of this outer coil and even direction. Again, resultant magnetic field must be 0. So again, two conditions. To be 0, resulting magnetic field, magnitudes must be equal. Magnitudes of magnetic fields must be equal. And second, directions of magnetic fields must be opposite. Okay, so then if direction of the magnetic fields are opposite, so currents must be opposite, otherwise directions cannot be opposite in direction. So direction of currents must be opposite. So in this case, magnetic field at the center of the coils can be opposite in direction. So if the directions are opposite, so it's possible to make the magnetic field at the center 0. Second condition, magnitude of the magnetic field must be equal. So the red coil produces a magnetic field here, and also blue coil produces a magnetic field here. These two must be opposite in direction and equal in magnitude. So let's make them equal in magnitude. So red coil, red. Remember equation for the magnetic field of the coil, mu I inner multiplied by n inner, number of turns of the inner coil, divided by 2 r of inner coil. This is the magnetic field of the red coil, which is inner coil at the center, must be equal mu I of outer current, outer coil multiplied by n of outer coil divided by 2 multiplied by r of outer coil. So mu over 2 and mu over 2 will simplify. So then we are going to write all other quantities, insert into the equation, and we will find the current of the outer coil. Inner coil has 6 ampere current. Let's write them. 6 ampere. Number of turns of the inner coil is 120. Radius of the inner coil is 0.0012, must be equal to current of the outer coil multiplied by number of turns of the outer coil, 150, and radius of the outer coil is 0.0017. There is just one unknown, which is the and out. Cross product you are going to apply, and you will find the outer coil's magnitude. I don't have a calculator right now, but I will tell you the result. So it is 6.8 ampere. So as you see, outer coil has a greater current than the inner one. Must be. Because if the radius is greater, current must be also greater to make the net magnetic field equal magnetic fields in the opposite directions at the center. So this is the solution of this problem. And these are other questions which are sent through the Viber. So this is the standard test prep of your book. Use the diagram below to answer the questions 7 to 9. So first one. What is the direction of the magnetic field B1 at the location of wire 2? So I1 makes a magnetic field B1 at this location, and we are going to find the direction of B1 by applying the right-hand rule. So let's apply the right-hand rule. Electric current is I1 is down to the plane of the page. So it's going to be like this. Curl forefinger at the location of the second wire is out of the page. So it must be out of the page. So it's going to be like this. So wire 1 produces a magnetic field at the location of wire 2. Magnetic field is out of the page. So apply the right hand rule like this. Thumb is pointing the direction of the I1, which is down to the plane of the page. Curled forefinger is fingertip must stay at the location of wire 2. So it's pointing the out of the page. Magnetic field of the wire 1 at the location of wire 2 is out of the page. What is the direction of the force on wire 2 as a result of B1? So this B1, because of I1, applies a force on wire 2. Again, we will use the right hand rule for magnetic force acting on a wire. Magnetic field is out of the page. It's going to be up to the sky. So electric current I2 is up to the plane of the page. So force is to the right. So force must be to the right. Answer is to the right. And even you can find that like this. If two wires carry in opposite currents, so they must repel each other. If they repel each other, one force must be to the right, other force must be to the left. You can do also by this way without applying right hand rule. And what is the magnitude of the magnetic force on wire 2? So wire 2 experiences a magnetic field F2 because of the magnetic field of the first wire, B1. Current of wire 2 is I2. Length of the wire 2 is L2. B1, I2, L2. B1, I2, L2 is the answer of this question. And last two questions sent through the Viber is from some Mr. Exam questions. Just one of the following expressions is true for Henry. Henry is unit of coefficient of self-induction, remember, L. We have only one equation for L. E is equal to negative L delta I over delta T. So this equation will help you to get what Henry is equal. Let L alone. So cross product, L is equal to negative E divided by delta I over delta T. And get this delta I over delta other side as division. So then L is equal to negative L del negative E divided by delta I over delta T. So Henry is L. E, volt. I, ampere. Delta T, second. So volt divided by ampere divided by second. This here, volt divided by ampere divided by second can be written like 1 over second. Because we know that 1 over second is hertz. That's why you can rewrite this. Henry is equal to volt divided by ampere multiplied by hertz. So the answer is volt divided by ampere times hertz or hertz times ampere. And the last one is just one of the following is equal to volt. So the opposite of this one. Here is the Henry is asked to you, now volt is asked to you. Yani E is equal to negative L delta I over delta T again. E is volt. L is Henry. Delta I ampere. And delta T 1 over second. 1 over second is hertz. So Henry times ampere times hertz is volt. Henry times ampere times hertz is equal to volt. These are the questions sent me through the Viber this night. I answered them all. I hope it will be useful for learning.